Is the density. Work is a change, some kind of change of the energy. And energy is the ability to do work. So basically that's what we call density. Energy can have different forms. The most important form is called the kinetic energy. Okay? It's the energy associated with the velocity or the speed of, precisely should be speed, of the object. So for an object, if it's moving fast, that means it has a larger kinetic energy. If it's not moving, then the kinetic energy is zero. And we call the kinetic energy here called K, or sometimes called KE. Okay, it's equal to 1/2 m v squared. Okay. Please note the important square here. Okay. So that means even you have a negative velocity, this negative side will be killed by the square. You still have a positive energy. Okay. From this calculation, kinetic energy can be either zero or positive, can never be negative. Okay. And then we also have the so-called potential energy. Potential energy, you have different kinds of potential energy. In this class, we only studied two kinds of the potential energy. The spring potential energy, okay, potential energy we use U. And for the spring potential energy, we can use US. And it's given by 1/2 K x squared. Okay, here K is a spring constant. Okay, if you have a spring, you know the spring constant measures how hard the spring is, the stiffness of the spring. Okay, so it will be given in the problem. You see, okay, and then you can calculate the spring potential energy. Question?
Is that spring or gravitation?
Okay, so there's mistake. Okay, so I just misplaced the two terms. Spring potential energy should be this, and gravitational potential energy should be this. Okay, so here, this is the spring potential energy. Okay, let's correct it quickly here. Okay, so the spring potential energy equals to this. And then for the gravitational potential energy, we call it UG. It can be calculated as mg multiplied by y. Okay. Now let's explain x and y here. X, this x is in fact is distance measured from the equilibrium of the spring. Okay. So it may or may not be along the horizontal direction. Okay. So let's say if you have a spring, when it's in the relaxed state, if you connect to a block, if the block at the relaxed state is here, if you stretch the spring to another distance, so x is the distance measured from the relaxed point. Okay, and then this is just a spring potential energy. Just this, if you stretch it, then you're going to have some potential energy. Or similarly, if you compress it. If you compress it to here, then this is also an x. Okay, always measured from the relaxed point. Okay, for both stretching and compressing, you will get the potential energy. And again, due to the square here, so no matter in which direction you are moving the object, you get the positive energy. Okay. So, okay, so we're here, the comment is that the zero reference point for the spring potential energy is always chosen as equilibrium position. So we always measure x from the relaxed point. And another thing is that even we call it x, actually it can be in any direction. If you can stretch your spring along this direction, then the relaxed place is here, then this is x. Okay, call it x just for simplicity. It could be in any direction. Now, but for gravitational potential energy, this y, okay, is different. This y is always vertical distance, okay? The vertical height measured from some point. So it says that, for example, this is your ground, this is the ground. If some object is here and the height made from ground is y, then the gravitational potential energy is mgy. Okay. But one comment here is that the zero reference point for the gravitational potential energy is arbitrary. You don't have to choose the ground as your zero. Okay? So for example, if this is the ground, if the height, okay, let's do that. If you have some building like this, the building is 10 meters, okay, we don't have, yes, 10 meters. And if you have a ball which is 5 meters above the building, okay, the top of the building, the mass equals to say 1 kilogram, g, we use 10. Now, if we try to calculate the gravitational potential energy of this ball, please note that you don't have unique answer. Your answer depends on where you are going to choose it as your zero reference. The normal choice may be if you choose 0 and ground, okay, then you can see that the gravitational potential energy Ug equals to mgy equals to 1 times 10 times what is the height in this case? 15 meters, so it's 115 joule. And you can choose any point as your zero. For example, if you choose here as your zero, the top of the building, if you choose 0 and top of the building, okay, let's calculate Ug equals to mgy equals to 1 times 10 times what is the height measured from the top of the building? 5 meters. Then in this case, the gravitational potential energy is 15 joule. Okay? This is completely correct. The value for the gravitational potential energy depends on your choice. Okay? In many cases, we may not choose the ground as our zero reference point. Okay? Especially, for example, if you consider some motion from here to here, then there is no reason to choose this as the zero. You can simply choose here as your zero. And later we are going to see that why it doesn't matter which they have different numbers. You are going to see finally what matters is not the absolute value of gravitational potential energy. What matters is the change in the gravitational potential energy. So if you just move from here to here, in any choice, the change will be the same, right? So doesn't matter. Finally, let's look at another concept called mechanical energy. The mechanical energy we label it as E is simply the summation of the kinetic energy and the potential energy. For any object, it may contain both kinetic energy or potential energy and potential energy. In that case, you have to sum them to give the kinetic energy. And here, this U could be spring potential energy, US, or gravitational potential, UG, or both. Okay, depending on the problem. So let's stop here.